Let's turn our attention to one particular chemical that exists in our atmosphere, and this compound is known as ozone. We addressed ozone back in chapter 1 lightly, but now we're going to talk about it a little bit more. Now, we can get ozone in two different areas within our atmosphere. First area we're going to talk about is stratospheric ozone. Stratospheric ozone is good ozone. We love it up there. The reason we like it is because it absorbs a lot of high energy ultraviolet light. So you get this high energy ultraviolet light comes in, it's absorbed by the ozone layer, while the rest of the light, the visible light, can pass straight through and reach the ground. Does it absorb all the ultraviolet light? No, it doesn't. But it does absorb a fair amount and keeps us from, well, literally cooking because of ultraviolet light. Now, where do we find this ozone? Well, here in the figure on the right, you can see stratospheric ozone is the highest concentration is right around an altitude of 25 kilometers or 15 miles. That is roughly where we see the highest concentration of ozone in the stratosphere. Okay, and we want to keep ozone up there. So how do you lose ozone? Well, no, let me ask it a different way. How does ozone protect us from ultraviolet light? That's a better question. Well, you have ozone, and then you have this ultraviolet radiation that comes in, hits the ozone. Well, then the ozone is going to split apart and form oxygen, O2, which is what we breathe, and then individual oxygen atoms. So O plus O2. And all of this happens right here in the stratosphere. So the ultraviolet radiation is absorbed by the ozone, and that energy excites the ozone to the point where it breaks apart and forms oxygen, molecular and atomic oxygen. Now, here's the issue. You've probably heard of the ozone hole. Here's how the ozone hole forms. You have other chemicals up in the atmosphere. They get up into the stratosphere. Not a huge surprise, and honestly, usually not a worry. Chlorofluorocarbons are one of those chemicals, CFCs. Chlorofluorocarbons, meaning they contain chlorine, fluorine, and carbon. They're not greenhouse gases, and by themselves, they're essentially harmless. They're just a chemical, nothing problematic. Not flammable, they're not toxic, and they're not stable. However, when you have ozone that breaks apart and turns into molecular and atomic oxygen, normally at night, when the sunlight's gone, they combine again to form ozone. So throughout the day, ozone is broken up into the atomic and molecular oxygen. And then at night, they recombine to form ozone. But unfortunately, the chlorine from the chlorofluorocarbons actually likes to react with the oxygen, in which case you get chlorine and oxygen combined together, and then you get oxygen left, and your ozone is not replenished. And so you end up with a drop in ozone concentrations. So you start off with a lot of ozone, it breaks apart through the day. At night, you get a lot of the ozone recombined, but if you have chlorine in the atmosphere, then that is going to prevent some of that ozone from recombining. You have a net decrease in ozone concentrations. That decrease in ozone concentrations is what we call the ozone hole. And so here you can see pictures of the North Pole in the spring and the South Pole in their spring, our fall, September, where where we're looking at concentrations of ozone. The redder the color, the more ozone you have. And then the deeper the blue and into violet that you get, the less ozone that you have. So you can see here, blue and purple are on the lower end of the scale. Well, this is something that happens naturally every spring. But because of the increased concentration of chlorofluorocarbons, the chlorine from the CFCs interact with the broken apart ozone and thus create a huge depletion, a much larger depletion in ozone concentrations. And so that's a good example of our ozone hole. It isn't really like a hole in the atmosphere where there's absolutely no ozone at all. It's just a depleted concentration of ozone, which of course worries us because if there's less ozone, then then fewer UV rays can actually be captured in the stratosphere. So this was starting to become quite a problem in the 70s and especially in the 1980s. We were seeing that ozone hole depletions were well out of hand. They were not good at all. And so a bunch of countries sat down together in Montreal, Canada in 1987, and they made an agreement to diminish the use of chlorofluorocarbons. And you can look here in this chart the amount of chlorine in the atmosphere. Ever since everything went into effect in 1989, and shortly after that, yeah, things kept rising as we started to make the adjustment. But after we made the adjustment, everything just dropped. So chlorine concentrations in the atmosphere have dropped significantly. And good news is that for the most part, our ozone hole issues have dropped to pre-1980 concentrations. So our ozone hole problem is going away. Here's one huge problem, however. The substitutes for chlorofluorocarbons are greenhouse gases. And so you switch from one problem to another. And that's something we'll address in a future video. Now, at the beginning of this video, I mentioned that there are two types of ozone that we needed to deal with. One was stratospheric ozone, the other is tropospheric ozone. When you have ozone in large concentrations around other chemicals, then you can develop what's called photochemical smog, also known as, and that comes from ground level ozone. Basically, you have sunlight that dissociates the ozone, which then eventually causes oxygen. Sunlight dissociates many of the pollutants, which then combine with oxygen to form ozone. And that ozone then builds up in concentration, building up large amounts of smog in cities. So you have the same process, but this time you introduce another chemical like NO2. NO2 is broken apart by radiation to form NO. NO would then the oxygen from that split then reacts with the molecular oxygen that we breathe, and it produces ozone. So yeah, kind of a problem. Thankfully, this is a reversible process. If you combine the ozone with the NO that we created earlier, that can get us back to what we had before, NO2 plus O2. So it is a reversible process. So that is the good news. Unfortunately, the increased production of nitric oxide, NO, and also ozone is not healthy for our bodies. So that is a huge worry here in the troposphere. And you can see here on the figure on the right, you have your stratospheric ozone that we talked about, but there's also this increased concentration near the surface of tropospheric ozone. And that's what produces this photochemical ozone that we are worried about. So that is a constant worry, and we're constantly trying to clean up our atmosphere to prevent tropospheric ozone from forming.